So today we'll get started by talking about special relativity. And so the question you might ask is, why do we special relativity? Because it's something that we already have been exposed before, and we know all that there is to know about the Lorentz transformation, length contraction, time dilation, and all these things. Well, first of all, we want to summarize it briefly so that we can remember what the basic formulas are. But more importantly, we would like to rewrite the fundamental results of special relativity in a way that translates into GR, right? And this is what is the next lecture about. That is, we are going to use essentially the same notation and the same kind of objects that we will use later in general relativity. So, for example, in the context of special relativity, we are going to introduce a metric which is called eta alpha beta, right? And when you write the Lorentz transformation and various quantities, like 4 vectors, in terms of this eta alpha beta, it looks like it's a lot of complication that is unnecessary. But it turns out that later on, it will save us a lot of work, because later on, this eta alpha beta, which is sometimes referred to as the flat metric, is going to get promoted to an object that will depend on x, right? And so we're going to be able to take over a lot of the formulas and just change letters here and there, but basically the expressions themselves will remain the same. So the first part of this class is going to be reformulate the laws of special relativity, and mainly the form of the Lorentz transformation, the energy momentum tensor, the proper time, and things like angular momentum and a perfect fluid, the energy momentum tensor for a perfect fluid, reformulate those in terms of these eta quantities so that we have expressions in front of us that we can just then promote to general relativistic expressions, right? And so this notation is something you have to get used to, right? So in particular, we're going to have indices which are upstairs and downstairs, which can be very confusing, right? So you can have indices that are upstairs, indices that are downstairs, and you will raise and lower them, and one might wonder, why in special relativity would you do anything like that? Well, generally we don't, but if you want to generalize to general relativity, you have to do that. You have to go through this gymnastics of having all sorts of indices which lie at different positions. It will make a big difference whether the index in GR, whether the index is upstairs or downstairs, right? So that is the motivation for all of this stuff. And so basically it's reformulating special relativity in the language that we'll use later on. So now remember that the Lorentz transformation originates from the following physical setup, where you have 2 observers, right? 2 observers, which we refer to as O and O prime, right? Which move at a relative velocity, which is v, and they observe at t equal to 0 that there is a light front going out from the origin, and they will describe the light front in terms of the relative coordinates. So observer O will say that x squared plus y squared plus z squared minus c squared t squared is equal to 0, which is the relationship between the coordinates and the time for a light wave, right? Now observer, so this is for observer O, right? Observer O prime will also observe pretty much the same relationship, except that everything will be primed for his coordinates, so x prime squared plus y prime squared plus z prime squared minus c squared t prime squared is equal to 0. So prime coordinates everywhere. And so this is coming from the constancy of light, right? C is equal to a constant, as is the same for all observers. So the observer O and O prime measure the speed of light to be the same, which is, of course, if you wish, the result of the Michelson-Morley experiment, and basically what Maxwell's theory tells us is that there is a unique speed of light that does not depend on the state of the observer. So now what Einstein realized, and perhaps Lorentz to some extent before of him, is that x prime is equal to gamma times x minus vt. So he said, let me try a linear relationship. A linear relationship, so that means that gamma is a constant, which relates x to x prime and to the time. And so now you can use this relationship to try to determine gamma, right? And this is an exercise that you do usually in your freshman physics or high school physics class. And you find out that the only way by which you can satisfy the first and the second equation is that gamma is equal to 1 over the square root of 1 minus v squared over c squared, right? That indeed you can have a linear relationship between the coordinates in the two reference frame, but that the gamma has to depend on the velocity. Right? And so we end up then with the Lorentz transformation, which I'm going to rewrite over here, which is x is equal to gamma times x minus vt, and that t prime is equal to t. No, t prime is not equal to t because that would not work, right? So you immediately realize that this cannot happen either, and that this is equal to gamma times t minus v over c squared times x. Right, and that you have this linear relationship between the two, and such that gamma, again, is 1 over the square root of 1 minus v squared over c squared. And this is the essence of the Lorentz transformation. The essence of the Lorentz transformation. And now in the case we're talking about, of course, we're in 3 dimensions, so we would have also y prime is equal to z, z prime equal to z, if v is along the x-axis. Right? So we're considering a transformation that is in a certain direction. In other words, we orient our coordinate system along v, and then that is the only thing that we do get in this case. So now we're going to reformulate, this is all well known, and so we're now going to reformulate this in a slightly different language that involves the Lorentz transformation matrix. Now before we do that, though, let me point out that this invariance property, this transformation law between coordinate systems that are moving at a uniform, right? Of course, it should be stated here that v is equal to constant, right? We don't have accelerations, right? So this is just a straight Lorentz transformation with v equal to constant. That go back a little bit and go back to Newton, right? Right now Newton had F equal ma, right? And that has also an invariance. Has an invariance too, but that invariance is not the invariance on the Lorentz transformation. The invariance is that x prime is equal to r times x plus b times t plus some x naught, right? And that t prime is equal to t. So Newton's equation has an invariance, right, which is similar to what we have there, but which does not involve a shift in the time, and it involves generally some sort of rotation. Right? And this is called Galilean invariance. Right? Galilean invariance because of the discussion we had about Galilei last time. Right? Galileo's point was that if you are in a ship and you do experiment in a ship, provided the Mediterranean is not too rough on that particular day, so that the ship moves like it is moving on a sheet of oil very smoothly, then you will not be able to tell the difference of whether you are on land or you are in the ship, because experiments will look the same. You can play table tennis or whatever it is. It would not be influenced by the fact that the ship is moving, right? And so this Galilean invariance is not an invariance of Maxwell's equations. Right? So after Maxwell wrote down his equation, and it was realized that whatever left those equations invariant was not the good old Galilean invariance, it was something else. And it is this. Right? So Maxwell's equations are invariant under the Lorentz transformation. So that's why the Lorentz transformation was discovered, if you wish, before even Einstein wrote down his special theory of relativity, because Lorentz and perhaps other people at the same time were fiddling about with trying to find a way by which you could change coordinates such that Maxwell's equation would maintain their form. And that is the transformation. This is a transformation that, in fact, you will find the proof of that. You find, for example, in Jackson, right, that The fields, of course, the E and B fields have to transform as well in a way that is not entirely trivial, but Maxwell's equations are form invariant if you apply the Lorentz transformation. They're not form invariant under the Galilean transformation. So, all right, so this is all the kind of old stuff, right? And so now we want to reformulate this, as I advertised before, in a way that carries over to general relativity, and at the same time is actually a little bit more elegant, right? Because writing out things in components is a real pain, right? So writing it out in individual components is not what we want to do. We want to condense all this stuff into something that is a little bit more streamlined. And so as a result of that, we're going to write the Lorentz transformation as in the following form, as x alpha prime is equal to lambda alpha beta times x beta, right? So we know that the Lorentz transformation is a linear transformation, and so this will be the case here as well, right? So that means that this lambda is a constant independent of x, right? And that will no longer be true later on when it gets to relativity, because all of a sudden the lambda will depend, in fact, on the position. But here it is a linear transformation, and because it is a linear transformation, of course, it makes dealing with special relativity much easier than it is when you extend the theory later on. And now, in fact, we can add to it something else. That is, we can add a translation. Right? If we add a translation, then again by a constant, that is no longer a Lorentz transformation. It's called a Poincaré transformation, and so we could do that too. But I think for the moment we can just dispense with that and worry about it later on. And so now the lambda has the following property, right? The lambda has the property that lambda alpha gamma lambda beta delta times eta alpha beta is equal to eta gamma delta. Well, what's this supposed to mean? Well, what is eta? Well, eta is a matrix, right? So let's write the indices. Eta alpha beta is equal to 1 if alpha equal beta equal 1, 2, 3. Minus 1 if alpha equal beta equal naught, and 0 if alpha is different from beta, which is the rest of the matrix. So in other words, if you write it as a matrix, eta is equal to minus 1, 1, 1, 1, and everything else is 0. Okay? So this is sometimes referred to, and we might as well do it because later on we're going to talk about metrics a lot. This is referred to as the flat metric. Right? Referred to as the flat metric. And so this is, as we'll see in a moment, this is a matrix or a metric that is very useful in calculating dot products. And so that's the first part of it, what this eta is. Now, what is the x with the index up? Well, x with the index up, of course, is what you would expect. That is just a combination of t and x, right? So this is going to be, as we'll see in a moment, a 4-vector, right? 4 vectors. So it is natural, of course, on the basis of what we discussed before, that you group the time and the spatial coordinate together into a single entity, which is this 4-vector, right? And then what happens is that this 4-vector gets rotated, right, by the Lorentz transformation when you act on it. Now, before well, let me say one more thing, that this is, in fact, as a matrix, this is, in fact, the same as writing eta is equal to lambda transpose times eta times lambda. Right? It's the same relationship. If you look at how these indices are summed over, and if you take this definition of the matrix, and by the way, again, because of what we're going to discuss later on in GR, we have to distinguish between indices which are upstairs and downstairs, so you have to get used to it. So this is definition of what this lambda is based on the form of the Lorentz transformation matrix we had a moment ago. Anyhow, this relationship that we have here is the same as that. Now, you do know that, of course, there is a property of matrices that we encounter often, which is this one, right? Namely that a matrix times its transpose is equal to 1. So what is the kind of matrix that when multiplied by the transpose gives the identity? That's, of course, a rotation, right? Rotations which form the orthogonal group have exactly this property, that lambda times lambda transpose is equal to 1. Now, in our case, it's not quite the same, but it's very similar, right? And the reason why it's not quite the same can be attributed to the fact that in special relativity, right, we have that x squared plus y squared plus z squared minus c squared t squared is equal to 0, and that we have this, for light front, that we have this minus sign, right? So this minus sign is kind of a plague that is going to follow us throughout the development of both special and general relativity. In fact, in general relativity, it will be less of a plague because it will be just one of the components of the metric. And so this minus sign is what gives rise to this slight agony, of having to keep track of all these signs, right? It accounts for the fact that we have this minus sign here is coming from that minus sign over there. Of course, there would be another way of dealing with this issue, and that would be to set t equal minus I tau, and then we would have x squared plus y squared plus z squared plus tau squared is equal to 0, right? We often also set the speed of light equal to 1, because luckily that is one of the things that we can do. There is no issue. We can choose a system of units where the speed of light is equal to 1, and we can get rid of that. And so this is, of course, something that we recognize even when you have a constant here, right? Because what are the transformations that leave the length of a vector invariant? Of course, it's rotations, right? It is precisely the rotations such that lambda times lambda transpose is equal to 1. And so this, in this case, you would have the orthogonal group. You would have the orthogonal group. So that means that if you define a complex time, right, and some of us have difficulties dealing with complex time, but of course if you pick up Steve Hawking's book, A Brief History of Time, he would tell you that your difficulty should be with real time and not with complex time, because complex time is so much more natural to him, to some of us, right? So anyhow, there's a big deal and big story about this use of complex time in quantum field theory as well, and so not just in gravity, but there is this interesting trick here, which is called the Euclidean rotation. Or sometimes called the Wick rotation. Right? There is this rotation that you can do, right? And this Euclidean or Wick rotation, and the fact that you could map the Lorentz group into just a simple four-dimensional orthogonal group, of course, in 4D, right? This was discovered by Minkowski. Right? So Minkowski was, well, one of Einstein's teachers, right, at the ETH in Zurich. So Einstein was his student. Minkowski was not enthusiastic about this student, but nevertheless, he passed his class. Later on, Minkowski, though, embraced the special theory of relativity wholeheartedly, and he contributed this insight that what Einstein was playing around with was basically a rotation group in four-dimensional space, and that you could show the analogy with the rotation group in a very clear way if you introduced a complex time, which you might or might not have problems with, but nevertheless, if you do it mathematically, they're identical. So this is a long-winded way to justify and explain why when we do Lorentz transformations in real time, we have to drag this eta along. We have to drag this matrix so that the time component always gets the right sign, right? And of course, if you're dealing with a complex one, if you're dealing with this one, then there is never an issue of getting the wrong sign, because then it becomes like three-dimensional rotations, except you have one extra dimension. So anyhow, so from now on, we are going to, I already set that up there, we're going to set c equal to 1. The c will disappear, basically, from the following lectures, and we will not see it again for quite a while. And so if we look at this relationship here, let's see what we still have to understand that this is actually correct and represents what we discussed so far. I mean, certainly the Lorentz transformation is a matrix, so it seems reasonable. But what we're going to prove next is that Lorentz transformations leave the proper time invariant. So what is the proper time? Well, the proper time is the following. So we are going to talk about infinitesimals, again, because it will be convenient later on for a number of reasons, and also in special relativity because we are going to calculate derivatives. So we need infinitesimals, and so we're going to define d tau squared, right, as dt squared minus dx squared, right? Now, just like we have dx, we have x alpha, which is t and x, we also, of course, have dx alpha, which is dt and dx, right? Because differentials act in a simple way on a vector, right? And so that means that when we write it in this way, we can, right, just to complicate our life a little bit, we can write it in terms of this matrix, right? Because this matrix is -1 along the first entry and then +1 along the rest. So that gives us nicely this relative minus sign, first of all. And secondly, everything else is 0, right? The off-diagonal matrix element is 0, which is precisely what we have here, because here, of course, we don't have any dt dx term either, right? So this is minus dx alpha dx beta times, minus 8 alpha beta times dx alpha dx beta. Okay, so it's the same thing. So this is our proper time interval. We can write it in terms of the metric, and we can write it in terms of the coordinate increments. And now we can take the differential of this relationship, which you're going to write underneath as well here. dx prime alpha is equal to lambda alpha beta dx prime dx beta. So why is this correct? Well, of course it's correct because this is just a linear relationship. So it just applies to the increments as well, because lambda is a constant, right? So that means that we can calculate d tau prime squared. Right, so now d tau prime squared is equal, right, this refers to observer O, and this refers to observer O prime that we discussed a moment ago. So observer O prime has minus eta prime alpha beta. No eta prime, because there is no such thing. There is only one eta, right? So it's just eta alpha beta again. But now, because we have a prime, we have to have here dx prime alpha, dx prime beta, right? And now what do I use? Well, I use the fact that these increments, right, I can read off from here. So I can read off one here and then a second one as well, right? So I can write this as minus 8 alpha beta, right? And now I use the matrix, lambda alpha gamma, lambda beta delta, times dx gamma, dx delta, right? Right, so I use here dx prime alpha equal lambda alpha beta dx beta, right? In both of these, right? But now I do know, what do I know? I do know that this right? This is equal, it's this, of course, and so it's equal to that, right? So this is equal to minus eta gamma delta times dx gamma dx delta, right? Because of this fundamental relationship right here, right? And in fact, this was the right one to use, right? This is the correct expression for a Lorentz transformation because indeed it does preserve, now we can see the proper time interval. Now remember that the proper time interval is what we started to talk about at the very beginning of the lecture, right? That was that x squared plus y squared plus c squared minus c squared t squared, which was the same, namely equal to 0 for both light fronts. So we conclude that if lambda satisfies the relationship that we have over there, then dt prime is equal to, d tau prime is equal to d tau, right? So the Lorentz transformation, which is what we have over here, with the eta defined, we should erase this because we won't be talking about anymore about orthogonal ones, right? So the Lorentz transformation, if it satisfies that, then the proper time intervals are the same, which is precisely what we need in order to make sure that we are talking about truly about the Lorentz transformation. So what else? Well, as far as Lorentz transformations are concerned, it is possible to discuss two types. So one more comment. Lorentz transformations can be proper or improper. So the proper ones are the ones that are, well, the mathematical term is that they're continuously connected to the identity. So it means that it's actually a smooth rotation, and when you take the velocity to 0, it becomes the identity. The improper ones are the ones that include odd things. Like time reversal and parity. Now, we discussed those in the quantum mechanics class, so you remember that in the case of time reversal, you just take t and make it go into minus t. In the case of parity, reverse x. Now, those obviously are not continuously connected to the identity because you really do a flip. And so they are Lorentz transformations too, but they're not the ones that we're really interested in. And so for most of the course, we'll just be focusing, as opposed to a particle physics class where one is actually quite interested in what happens when you have this kind of parity transformation and time reversal and charge conjugation. So for here, we'll be just focusing on the proper ones, which are the ones that are nicely behaved and look like true rotations. Right? So the ones that are improper have a determinant which is equal to -1. So we can always tell which one is which. So now, the Lorentz transformation contain, in principle, rotations as well. That is, the Lorentz transformation I wrote down at the beginning of the lecture was one that is usually referred to as a Lorentz boost. That is, you consider one reference frame and then another one which is moving with respect to the first one at a given velocity v, which is fixed. But in fact, there are more general Lorentz transformations which satisfy the same kind of constraint that I just erased on the other blackboard, right? Which are basically orthogonal type transformations. There's other transformations which include a rotation as well. So you do a Lorentz boost and then you rotate the frame also a little bit. Right? And so those are also legitimate Lorentz transformations. So rotations are also special cases of Lorentz transformations, right? And so they have the form that lambda, well, as you can imagine, of course, what they change is the x. right, which we are going to write as xi, right, where I runs from 1 to 3, obviously. Right, so they change the x, and so they're also special Lorentz transformations, and they lambda ij is equal to some matrix, which we refer to as Rij, which is a good, honest rotation matrix, which, for example, you can parameterize by a set of 3 Euler angles, if you wish, or by some other way of parameterizing. And so now this is, of course, just a 3 by 3 matrix, right? Because I and j run from 1 to 3. And so what about the remaining components? Well, the remaining components would be the lambda I naught and the lambda naught naught, right? And well, if this is a good, honest, simple rotation, then it doesn't do anything to the time components, right? So the lambda I naught would be equal to 0, right? And would be the same as the lambda naught I. And the lambda naught naught just would be equal to 1. Right? Lambda naught naught equal to 1. So a rotation is a special case of a Lorentz transformation. It falls into the same class. And so the question then is, what is the general form of the Lorentz transformation? And well, we will not do all of the derivation here. You can find maybe a little bit more details in the book. And before, remember, we just gave the form of the Lorentz transformation when you do the transformation in the x direction. Right? So general form of a Lorentz transformation is that, and so we're going to write the case of a boost only, namely no rotation, right? But still general, because we are going to have an arbitrary v. And in fact, this will be very useful later on to have it, right? So, well, if v is along the x-axis, then it has to reduce to what we had before. And so you can easily guess what it has to do. First of all, the lambda naught naught is the way same it was before. And so that is equal to 1 over square root of 1 minus v squared. Notice that we're using a system of units where c is 1, so the c has disappeared, right? And this is what we usually refer to as gamma, this gamma factor, right? And so that's the first entry. And the lambda I naught is equal to gamma times vi, right? And so that, of course, reduces to what we had before, but we're still left with a number of other entries. In particular, we need to know what the lambda ij is, and those can be obtained by the fact that the lambda is an orthogonal matrix, right? And so the orthogonality constraint tells us that this is equal to lambda ij is equal to delta ij plus vi vj times gamma minus 1 over v squared. Right? And this is something that you might have seen, in fact, already at the undergraduate level. And, well, that's not all of it, because we also need the lambda naught naught. Well, I already have the lambda naught naught, so that's all there is to it. So this is the most general form of Lorentz boost when v is not along any given axis. So we can write this in matrix form if you want, right? So we can write it as a matrix. So as a matrix. Right, so as a matrix lambda. So it's some big 4 by 4 matrix. So the first entry is let's take the II components, right? So it is 1 plus Vx squared, right, times gamma minus 1 over V squared, and then Vx Vy times gamma minus 1 over V squared, and so on, right, and so on, right? Let me write this matrix element here. It's a symmetric matrix, so it's Vx, Vy times gamma minus 1 over V squared, right? And then the diagonal matrix element is 1 plus Vy squared gamma minus 1 over V squared, right? So dot, 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 and then at the very last row and column, we have the lambda naught naught, which is equal to gamma. And here we have also a gamma Vx, gamma Vy, dot, 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 and then gamma. Right? And that's our matrix. So you can always write it as a matrix. The question is whether really your life gets simplified by the fact that you write it as a matrix as opposed to just writing it in terms of its components, which sometimes is actually easier to manipulate. So now if you see, if you look at the original case was Vy equal Vz is equal to 0, right? And then Vx is the same as V. That's the case we discussed at the very beginning of the lecture. Then, of course, everything that has a Vy or a Vz in it, like this term, is equal to 0. And so then we have that lambda is equal to gamma 0, 0, gamma V, and then 0. We have a 1 along the diagonal, 0, and another 0 here, and then 0, 0, 1, another 0 here, and then gamma V, and then 0, 0, and 1 at the bottom. And so we get this 4x4 matrix, right? And so this is the matrix that has all the properties that we discussed so far, and is an explicit form of a Lorentz boost. Sorry, gamma. Sorry for the last entry. Thank you. So now we can discuss a few more things that you've seen before, but which we can formulate in this new language, which has the lambda alpha beta matrix. All right. So try to use this lambda alpha beta, right? So we have that x prime alpha is equal to lambda alpha beta x beta, right? And which is nice and shorthand, and so we know what the lambda matrix looks like because we have said everything that there is to say about it. And so the next thing we can discuss is time dilation in this new language, right? So again, we will be referring to an observer O and an observer O prime, right, which are moving with respect to each other with a velocity v. And so the first observer is at rest. The first observer is at rest. So that means that its increment, right, its increment. So there is a nice way of writing these things down in terms of differential, namely that its increment is equal to 0 because it's now moving, and its time interval, its proper time interval, is equal to, its time interval, dt is equal to delta t. So where delta t is just the rate of some clock. So ticking of some clock. And so what we want to do is compare the clock for one observer to the clock for the other observer. And we will find that the ticking does not proceed at the same rate in the two cases. Now, still, for the first observer, we can calculate this d tau squared. Now, why do we calculate the d tau squared? Of course, that's the proper time interval, right? And it gets squared because it will be convenient to just calculate the square. And what we have found before is that the proper time interval is the same for two observers which are related to each other by a Lorentz transformation, right? So we do know that d tau is equal to d tau prime. We're going to make use of that in a second, right? And so we write the d tau squared. Right? Actually, let me write the d tau and take the square root. So d tau, remember, was equal to the square root of dt squared minus dx squared. right? But of course, in our case, the dx squared is 0, and the dt is equal to the period of the clock, and so we just get the proper time interval is the same as the clock interval, right? So in other words, in the frame that is with the observer, moving with the observer, and the frame that is not moving at a velocity v with respect to O, the proper time is the same as the time, right? Because the increment dx is 0. And now we look at the other observer, and so for the other observer, it's of course described by a prime coordinate system, and now it is moving with respect to the first one, so we know that dx prime is equal to v times dt prime because of the movement, right? And so this is going to be true, and so as a result of that, we can calculate again the proper time in this case, right? The proper time is the square root, right, of dx prime squared minus dt prime squared, right? And sorry, the other way around, dt prime squared minus dx squared. I should come back to that issue of conventions in a second. So dt prime squared minus dx squared, and so this is equal. So now we can factor out, right? You replace the fact that the dt and dx is related to this relationship, and so we can write this as square root of 1 minus v squared times the interval delta t, right? And so, sorry, times dt prime, right? And these two have to be the same. Right? They have to be the same because this is a property of the Lorentz transformation, that it keeps the proper time interval the same. So that means that dt prime is equal to 1 over the square root of 1 minus v squared times this proper clock interval, right? So there is a time dilation factor which comes in, and which is this, again, given by gamma, right, or this gamma factor, right? Now, about notation, you see this sign. So comment on conventions, right? Comment on conventions is that in some books, proper time intervals are defined with the opposite sign. So in particular, eta alpha beta here is equal to, we said it was equal to -1 and then 1, 1, 1 and 0, right? And so we have a -1 for the not component. And in some other books, so elsewhere, we have that this is equal to 1, -1, -1, and -1 and 0. So just to add to the confusion, the use of eta, the form of eta, is not always the same. In particular, Einstein's original paper, 1916, uses this one, right? And well, Weinberg uses that one, but sometimes the second one is referred to as the particle physics convention. Particle physics convention. And usually GR books have the top one, even though there are exceptions. So if you think that if you pick up a book and you find that the proper time interval is defined, for example, or some invariant distance is defined with a different sign, then you might have to do something with the conventions that are used. And many books nowadays list these conventions at the very beginning or back of the book, so you can find exactly what they define this eta to be, so that you don't get confused about signs, because otherwise the signs are going to be quite different throughout the book. In fact, even the very definition of some of the fields that we'll encounter later on, like the Riemann tensor, define sign between Weinberg and, say, Misner-Thornwheeler, for example, which of course initially can lead to quite a bit of confusion. So anyhow, we're going to stick to the top one, and so we don't need to remember anything about this. Of course, the less number of minus signs you have, the better it is, I would think, right? Less chances for errors. I mean, this is a very good way of introducing all sorts of mistake into a calculations, having these minus signs floating around everywhere. And in fact, that is one of the reasons why some people like Toft, for example, in the lecture which I posted on the webpage, prefers to use the complex notation, because with the complex notation you don't have minus signs. Everything is plus. Everything is, and so he claims that this is, and he must be right, of course, but he claims that this is less error prone if you do it that way. So anyhow, here we have only one minus sign, so whenever we have a time component, we have to worry whether we got the sign right or not, and then the spatial components we don't need usually to worry about. So now we come to the next topic. I mean, there's also length contraction, but length contraction goes pretty much the same way. So we don't need to, this is just as an illustration of how the conservation of the proper time interval under a Lorentz transformation is useful in calculating simple things like slowing down of clocks. So the next thing I want to talk about is particle dynamics. Right. Well, of course, in the good old days, this used to be F equal ma. Right. So before the advent of special relativity, you would just write down Newton's equation, and you would know exactly what the two sides mean, right? Because given a mass, the a is just the acceleration, the second derivative of the coordinate with respect to time, and the force is some given force, right? And so now we want to generalize this to something that is Lorentz invariant. Right, in some way. In fact, it would be Lorentz covariant, but let's not pick about details in this case. And so it means that we have to formulate it in terms of 4-vector. So like, for example, x alpha, and there's going to be a few more, right? Right. And well, but we know that in some limit it should become the good old Newton's equation, right? And so the candidate form if you think about it a little bit, is easy to write down. Well, first of all, the force. Okay, well, the force, we want to write things in terms of 4 vectors, so it cannot be the F by itself, it has to be an F alpha, right? Where alpha is 1, 2, 3, and the time component, which you can call naught, or you can call 4, it doesn't matter, right? So this is going to be our force, and of course we'll have to determine what that exactly looks like, and we'll do that in a moment. And that is going to be equal to the acceleration times the mass. Now the mass is just a parameter, so there's no reason to fiddle with that, so we're just going to copy that over. And what about the acceleration? Well, the acceleration is the second derivative, right, of the coordinate, second derivative of the coordinate with respect to time, right? So we would write it in this way, because the coordinate, of course, gets extended to a 4-vector, right? X alpha is equal to x and t, right? We can put sometimes the t at the beginning or at the end, it doesn't matter, right? But the problem, of course, is the bottom, right? Would be dt squared. The problem is the bottom because the time, right, depends on what observer we're looking at, right? So this is no good, right? So we can't use the time. The top is all right. The bottom is not, right? So we have to use something that is going to be the same for observer O and observer O prime. And there is a good candidate for that, right? And that is the proper time. The proper time, right? The proper time, so d tau squared, right? So this is the proper time, which we've defined a moment ago, right? After all, remember, derivatives are handled just like you have ratios of objects constructed in the way you construct a fraction, right? So we have defined before, right, the d tau, right, in terms of the flat metric. So we also know that this proper time is an invariant, right? Because we know that d tau prime is equal to d tau. So that means that it's a good thing to use, Right? It's a good thing to use because it doesn't change from observer O to observer O prime like the time would. Right? The time would go from t to t prime. The proper time does not. So we have a good candidate equation to describe particle dynamics in terms of 4 vectors. And so that means that now, in principle, and we haven't written down what the force is yet, right? So the force is to be determined. Right? But let's assume that we do know what the force is, then we can solve this equation just like we solved Newton's equation to find x alpha of tau. Right? We can find x alpha of tau, which is given by something. Right? We get a closed expression for this. And from that, we can now write down the analog of Newton's equation. And how do we do that? Because it looks like we have 4 equations here, right? In Newton's case, we just have 3. So as soon as we try to generalize the equation to particle dynamics to a relativistic context, we end up with an extra equation, right? Which is the not equation, right? The equation where alpha is equal to 0. So what is the role of that not equation, that extra equation? Well, the role of the not equation, it gives something that we need. Can you see what it is? It gives us the relationship between tau and t. Right? It gives tau as a function of t, or t as a function of tau, which is the same thing. Which means it allows us to eliminate tau. Right? So in fact, we do have an extra equation, and we need an extra equation because that extra equation allows us to eliminate the proper time in favor of the real time, which is right, the second derivative of the coordinate with respect to the time associated with a given observer, right? So we don't want the tau, we want the t, and that is why we have an extra equation. All right, so what is f alpha? But, right, what is F alpha, right, which is this 4 force, right? Some sort of 4 force, right? So we would think, right, naively at first, we would think that F alpha, right, has 4 components. Well, one, of course, is the F naught, and the other one would be the force, right? And so that might be a first try, and of course it's incorrect, right? It's not quite as simple, right? Not quite as simple because there needs to be some gamma factors, right? There needs to be some velocity that enters into this thing. And so that means that we are going to write, so we're going to first consider a particle momentarily at rest, right? And so if the particle is at rest, then d tau is equal to dt. Why is that? Because, of course, dx is 0, right? There is no increment in space. And so then this second derivative is just the derivative with respect to the ordinary time. So in this case, f alpha goes indeed into f. And we determine that the second component is not, right? Second component is not. And so that's one piece. So we know that when a particle is at rest, it has the form of this 4 vector. And so what can we do to promote a 4 vector that is known in a given frame to a form that is valid in any frame? Well, all we need to do is to apply to that 4 vector the explicit form of the Lorentz transformation that we wrote down before, because that's how you take an object that is at rest and you give it a velocity v is by applying a Lorentz boost. So apply Lorentz boost to the above. Right? And so that means that we look up the Lorentz boost. So F alpha has to be a 4-vector, right? Because if it's not a 4-vector, then the equation is not invariant. It depends on what frame you're looking at. So if it is a 4-vector, then it means that F prime alpha is equal to lambda alpha beta F beta, right? Where this is a Lorentz transformation, right? Where lambda alpha beta, right, depends on some velocity v if we consider this to be a boost, which is all that we need here, right? And so what we do is we take here F alpha and write it as lambda alpha beta times F beta, where F beta is this thing here. Right? So we apply the Lorentz boost to the expression that is correct at v equal to 0. And so we get exercise. Right? So remember, the Lorentz transformation was fairly simple, right? Lambda ij is equal to delta ij plus vij times gamma minus 1 over v squared, right? We wrote that down. So all you need to do is do this by components, take into account that f naught in this case is 0, right? And you get that f so you get that f has the following component, that the spatial component f of little f is equal to the original force, right, which is this one here, right, the force for a particle at rest, plus the Lorentz boost part, right? And the Lorentz boost part is plus, so there's this factor, remember the factor of gamma minus 1, and then there is the vij, which gives v times v dotted into f, and then there is the gamma factor, the additional velocity factor, which is 1 over v squared, right? And what about f naught? Well, f naught, remember, when you act on a matrix, on a vector that has an entry which is 0, you don't get 0 again, you get some non-zero matrix element. So the naught component of the little f is non-zero, and it is equal to gamma times v dotted into f. And so this is equal to, actually, this is just equal to v times the above f. Because then the v squared cancels out, and you get the gammas that go away, and you get just the velocity times f, right? So this goes in there, right? And so we're done. So we're done because we have been able, so let me write it down again. We have been able to write, what have we achieved, right? We have been able to write an equation which is that F alpha is equal to the mass times the second derivative with respect to x alpha of d tau squared, right? We have been able to write down an equation which is the analog of F equal ma, which is has the property that 1, it is Lorentz invariant, right? It is actually Lorentz covariant, but in any case, it's a Lorentz invariant form. It looks like everything that appears in it is a 4-vector, right? Which means that if this equation is satisfied in one frame, it will be also satisfied in another frame where you replace the x by the x prime and the f by the f prime. Right, it is Lorentz invariant, and what is the second property that it has? It reduces to this original equation when the particle's velocity goes to 0, right? So it reduces to old result in appropriate limit, right? So this is actually an example of a procedure which we're going to use over and over again, because we are going to be confronted in a number of instances of what do we write down for equations in not only special relativity, which is easy, but in general relativity. How do we generalize, a Maxwell's equation? Well, that is already invariant, so we don't have to do a whole lot of work. There's some slight issues here and there. But how do you generalize, the equations for a fluid, for example, in general relativistic context? Well, you're going to play the same game. That is, in other words, you're going to write down something which is manifestly invariant, and then you're going to go to a frame where you actually know what the form should be, right? Non-relativistic limit, for example, and that will fix, right, the coefficients of various terms that will generally uniquely determine what the form should be. So it's a very nice way to proceed, and we are going to use that in a number of cases. So we talked about the force equation, and another thing that we do use occasionally is energy and momentum, right? So let's talk a little bit about that as well, just to see how it works out in this particular framework. So energy and momentum. So again, we do know what these things look like if we have a non-relativistic particle. And so we have the P and we have the E, right? And so the temptation is to promote that to a 4-vector in this way, right? And then we think that we want to define the 4-vector P alpha, right, in terms of derivatives of the coordinates, right? Because the momentum is m times v. So that would indicate that we would write this as dx alpha by dt. Again, this is wrong and will not work because the t depends on the observer, right? And so the only candidate to use that is invariant for a time derivative is going to be our tau. And so we should define it in this way. And if we define it in this way, then this is an equation for a 4-vector. Right, this is an equation for 4 vectors, which means that if it is satisfied in the frame O, it will also be satisfied in the frame O prime, where you place all coordinates and p's and so forth by their prime counterpart, right, with the d tau being invariant, right? And so we can write the equations of motion we had a moment ago. We can write that as dp alpha by d tau, right, is equal to our 4 force, which is F alpha, right? So we can add that to this, and of course it's just a rephrasing. So now if you really want, you can replace the d tau by the time increment, right? And so we write d tau as we have done already before in terms of the interval as dt squared minus dx squared. Right? You can write it in this form. And now what we do is we divide by dt twice, right? So we divide by dt squared and multiply by dt squared. So you can write this as dt, right, times, of course, what's left in the square root is a 1 for the first term, because dt squared divided by dt squared is 1. And then for the second term is the velocity, right, because that's dx by dt. Right, so v is, of course, equal to dx by dt. Right, so this is equal to dt times 1 minus v squared to the 1/2. And this coefficient here is, of course, gamma to the minus 1. That's the gamma factor that we introduced a moment ago. And so that is interesting because it tells us something that we are going to use once in a while, that d tau is equal to gamma to the minus 1 times dt, or that d tau by dt, or dt by d tau is equal to gamma. dt by d tau is equal to gamma. Right? So, well, who cares? Well, we do care because we can write now we can write then that dx alpha by d tau is equal to dx alpha by dt times dt by d tau, right? And dt by d tau is right there, it's the gamma. Okay. So that means that you can now write the two ingredients of the momentum expression in terms of the gamma, right? So we split up the alpha equal 1, 2, 3 part and the alpha equal 0 part, right? The alpha equal 1, 2, 3 part is the spatial component of the 4 vector, which is just a p. Right. So we have that pi is equal to m gamma times v. I, let's write it in components, I, right? And the naught component tells us that the energy is equal to just m times gamma, right? And so this, of course, is the standard. Again, remember, we don't have mc squared because we set the speed of light equal to 1. So that's the standard Einstein relationship of momentum and so forth, expressed in terms of the velocity. So we can now, of course, replace these two things and write, for example, that e squared is equal to p squared c squared plus m squared c to the 4th. If you put the speed of light back in, that's just by elimination from those two. So that is what we learn if we look at the momentum. So let's continue with kind of the formal development, right? Because that is going to be very useful and important when we go on and move on to the theory of general relativity. So let's talk a little bit about scalars, vectors, and tensors, right? And so this is all in 4 dimensions, right? So all the indices we're going to have now are going to run from 1 to 4 or 0 to 3. And so we have learned that we have this fundamental Lorentz transformation, which is x prime alpha is equal to lambda alpha beta times x beta. Right? So that was the transformation law for the coordinate, right, where lambda alpha beta is a function, for example, of v for boosts, right? And if it's not a boost, then it would contain a rotation as well. And so that's the fundamental law for the coordinate. And so in general, for a 4 vector, we define or have, right, a similar transformation law. So we define a 4 vector, anything that transforms the same way, right? So this is going to be some general vector, and we can call it v, right? So we take a vector v alpha and we do a Lorentz transformation on it, right? Lorentz transformation on it. And so it could be the coordinate, but we have seen already that we have several other objects because we had the second derivative of the coordinate and the first derivative, which are both 4 vectors, as well as the energy momentum 4 vector. So any of those will work. And so this will become a v prime alpha, which is lambda alpha beta times v beta. And that is the transformation law for a vector. So anything that transforms this way is going to be a 4 vector. Now, well, it's not quite as simple because this is actually what is referred to as a contravariant vector. Contravariant vector, because we can define something else. So an example is of course x alpha. So we've seen an example of that. But we can define something that is slightly different, and that is something that, so it's case 1. Case 2 is a u alpha, which under a Lorentz transformation transforms into a u prime alpha. And that u prime alpha transforms with a slightly different form of the lambda matrix, which is lambda alpha beta u beta in this way. And this is called a covariant vector. Covariant vector. Right? And that's something that, well, we haven't quite seen yet, but it transforms in a slightly different way, and we have to now have to tell you what this matrix is. Right? So what is this matrix? Because the position of the index is different, right? And so it looks like it's something that is different, right? And so where this matrix, this new matrix, okay, so we're going to copy the indices exactly as we have it here, right? So we have lambda alpha beta position in this way. And so this is equal to eta alpha gamma, eta beta delta, and then times lambda gamma delta. Right, so this is the new one, and this is the old one. Right. So it is not quite the same, it is similar. And what about this symbol here? Well, the symbol here is the same. So eta alpha beta is the same as eta alpha beta when this is down. So that's exactly the same matrix. Now remember that this matrix eta was equal to -1, 1, 1, 1, and then 0 everywhere else, right? So formally the two are exactly the same. And so now, are the two the same? Is this lambda the same as that lambda? Well, you can immediately do a little bit of exercise with some given lambda matrix. You'll find out they're not the same. They're slightly different, right? And now, in the case of special relativity, you actually don't have to go to this complication of defining covariant and contravariant. You can do a lot of very neat and simple, sorry, did I say general? I meant special. Special relativity you can do without the contravariant and covariant. But in general relativity, you need both. And it's essential because we'll see in a moment that in general relativity, one matrix becomes the inverse of the other one. The one index is up is the inverse of the one with indices down. They're completely different objects in principle. Right? So we have to go through this agony of defining contravariant and covariant vectors because that is going to be very useful and very important later on. And now you can show, right? One can show the following, that one can do the following exercise, that lambda, so this involves a few indices, like lambda alpha gamma times lambda alpha beta, right? So you take this product and you sum over this index, right? Whenever repeated as indices appear, they're summed over. So now one is the, right, this is the matrix we have up there, and this one is the original one that we have here, right? So we're talking about two slightly different objects. Where you position the indices is crucial, so you can't just move them around. They have to be in a specific position, up or down, left or right. And, well, you can use, of course, any label you wish, right? You can call them A, B, C, or you can use mu, nu, rho, and so forth. So now we can simplify this expression because we can use what we have here, right? We can use what we have here. So this is going to be eta alpha gamma. And, well, we cannot use gamma because the gamma has already been used here. So there's going to be a dummy index which we give it a new name called delta. So eta alpha delta times eta gamma delta. And again, we need to use a new name. So we're going to call it gamma epsilon, right? Again, the delta has been used here once. Right, so we use epsilon, and then lambda delta epsilon, and then times lambda alpha beta, which we just copy over, right? And, well, that is precisely, if you look back, this part here, if you look back a couple of blackboards, that is exactly the expression that we called eta eta epsilon beta. So this is equal to eta epsilon beta times eta gamma epsilon, right? And it's summed over epsilon. So it is delta. So what is the product of two of these eta matrices? Well, the product of two eta matrices is a diagonal matrix because the eta has a -1 here, but when you multiply with itself, the -1 becomes a plus sign. So this is delta beta gamma. So this is essentially the identity matrix, right? The identity matrix. So what have we discovered through this exercise of playing around with indices? We have discovered that the product of that matrix, right, with indices arranged in this way, and the product of that with this other matrix, which we define in this way, which applies to the transformation law for covariant vectors, the product of the two is equal to the identity, which means that, of course, one is just the inverse of the other one, right? So this is, okay, so we refer this as the inverse of the lambda alpha beta, right? Right. So again, in special relativity, usually you don't want to go through this agony because you are basically playing with matrices that are almost the same because you're just multiplying by things that are diagonal with perhaps, well, the only thing is really to have a -1 up there. But it's really an unnecessary complication in most of special relativity. But in general relativity, they will be different. So they will be fundamentally different. And so in GR, lambda and lambda to the -1 are fundamentally different. Fundamentally different, okay? And so we will have to deal with this, and we will have to make this distinction between covariant and contravariant vectors. And I think this is an excellent place to stop, and we're going to continue on that next time.